Hello, everybody. Welcome to the Rocky Mountain Mathematical Physics Seminar. Our speaker today is Howie Jordan from the University of Colorado, Boulder, and he will speak about categorical partition logic for quantum information. Thank you. So please.
Yeah, thank you, Marcus. So the topic is partition logic. I won't get to say as much about the categorical aspects as I want to. I'll hint at some things at the end, but I still have some open questions. So, a big chunk of it will be an introduction to this idea of partition logic. So, partition logic for quantum information. The motivation here stems from a duality we can notice between probability and information theory. Okay? So, pretty simple fact that probability is assigned to subspaces, right? We assign some probability to a subspace, or sorry, to a subset, really. Okay? And there's this older notion of so-called logical probability, due I think mostly to Boulder. But this is just the familiar idea of taking a subset and taking a subset A of some universe U, right, and saying that the probability should be the ratio of the number of things in A to the number of things in U. I'll call that like logical probability, since it's sort of just directly taking the logical operations on subsets and treating them like operations on an event space for probability. And of course, the sort of classical probability theory extends this to arbitrary Boolean algebras. Well, not arbitrary, we restrict to at least countable completeness, but still, Boolean algebras of subsets. Okay? So, the duality that we can notice is a duality really between the idea of taking subsets as your main objective focus and comparing that to what we do in info theory, where the thing that's fundamental is, I'll say, a partition. The sort of overall point of information theory is that information is embodied in your ability to make distinctions between different outcomes. Okay? So having a partition of your event space in some sense tells you how much you can differentiate between these different events. So we have our sort of classical notion of information. I'll just say I of A, log base 2 of 1 over the probability of that object A. This is sort of the original version due to Shannon. And the idea here is that by taking the log base 2 of 1 over this probability, we're determining how many binary partitions, how many yes/no questions we need to ask and get an answer to in order to distinguish an event uniquely. So this is sort of that number of binary partitions. And of course, if I change my base 2 to whatever, it's some other type of partition. Okay? And subsets are dual to partitions in a precise categorical sense. In the sense that in a category, we represent subsets really by monic maps, aka injection maps, we can also say. Right, so I have my set A and I have some monic injecting it, witnessing it as a sub-object of some other object U. And we can compare that to the epimorphisms, which are essentially the surjections. Sort of a slight generalization of surjection. Okay? And the surjections, of course, if I take U and I surject onto some, I guess I'm going to resolve this. And I surject onto some set A, then I think about all the little objects of A as sort of representing some equivalence class that corresponds to everything in the pre-image under this surjection. So I'm kind of using the fact that I can identify a partition of my set, a breakdown into a bunch of subsets that don't overlap but exhaust the space. I can always represent that as the sort of corresponding projection map sending an object to its equivalence class or to a representative of its equivalence class. So this is the sense in which there's a natural categorical duality between subsets and partitions. And the motivation, or maybe I should say that that idea motivates the work of David Ellerman, who has turned this idea into a more precise relationship, which we'll elaborate on here. So, for some finite set for now, I'll mainly just deal with finite sets, at least for today. I'm going to denote by part of U the surjections with domain U. With domain U. Okay? First thing that we want to know about this is that just like we get a nice logical structure on subsets, they behave just like a Boolean logic. The partition lattice, well, the partitions form a lattice. Spoiler. The partitions also form a lattice. So they have meets and joins, which act like ands and ors. It's a bounded lattice, so it has a sort of truth object and a falsity object at the top and bottom. And we can kind of interpret it as a sort of logical system in the same way that we interpret subsets as a logical system. I'm not going to go through every detail of the proof, but I can just kind of outline it as sort of a follow your nose kind of thing and just figuring out what the least upper bounds and greatest upper bounds should be. But the order relation, if I have a set U and I have two different surjections, if I have a surjection that factors through, say from this object X to this other object Y, then I will say that my surjection onto Y is less than the one onto X. Sometimes I'll write Y less or equal to X. Sometimes I'll denote with a pi that it's the projection map that I really care about. I'll probably not be as consistent with that as I should be. So if I ever write something that doesn't make sense, feel free to stop me. But that's our notion of ordering in this lattice. Anytime I can factor one of my projections through another one, I say that the other projection, the smaller set, the smallest set in this set sequence of surjections, that's the smaller partition in the sense that the bigger partition is a refinement. So we would also say that Y is refined by X. And so what's really going on here is my map onto X creates a bunch of equivalence classes, identifies a bunch of objects in U, and then I subject onto Y and I identify even more of those. So X is more refined in the sense that it makes less identifications than Y does, than the map onto Y does. Okay? So the lattice structure falls out pretty nicely, right? I said it's bounded, so I should mention that there's a top and a bottom element, but they're not too bad. Given the way I set up the order, the identity map from U to U is the top partition, the most fine partition. Every object is distinguished from every other. And the bottom element is the unique map onto a singleton set, or whatever terminal object I happen to have. So there's always a surjection onto that. Every other surjection can factor through, or yeah, every other surjection can factor through this. So this is the least fine partition. I kind of like the name that Ellerman gives this. He calls it the blob partition. Everything's stuck together and we can't tell anything apart. Okay? So the more interesting things are the meet and join. So meet sort of like an and of some kind. How am I going to create this for these partitions? We take every subset of my big universal set that can be written as a union two different ways. One way with, I guess I should give some names to what I'm meeting and joining here. We'll say X meet Y and X join Y. So X meet Y is a new partition constructed by taking any subset that can be written both as a union of blocks from X and a union of blocks from Y. So these little X's and little Y's, it's some subset of X and Y, some subset of the equivalence relations, or some subset of the partitions. And anytime I can take a set and I can say, okay, well, on the one hand, it's a union of partitions here. On the other hand, it's a union of partitions there. Then I join them together as one big partition. And I create this less refined object. So if it's a meet, it's a greatest lower bound. It sits below them in the order that we gave. So it's a less refined partition that's identifying more things. I think the join is probably a little bit more interesting, at least conceptually. We take here instead the intersection of any two blocks. So by B sub X and B sub Y, I just mean some block in X and some block in Y, some block of the partition. We just take all the non-empty ones, right? So this one's a refinement of the two that we had. And so what we're doing is we're saying, okay, well, X gives me some sense of distinctions I can make between the objects of U. Y gives me some other sense. If I join these two together, I should be able to make more differentiations than I was able to before. So I take the intersection of two blocks whenever it's non-empty and say, okay, well, I can kind of use X to differentiate the things in the X part of the block from other things in other X blocks. And I can also use the data from the partition Y to differentiate it between everything else in the other partitions that Y has. Okay? So this is the sort of basics of that lattice that arises naturally as categorical dual to subset lattices. Okay?
Howie?
Yes, sir.
So for the join, I think if I'm doing this right, this is the same as like taking the map to X cross Y, right? And taking the partition you get from that.
Yeah, that's yes, yes.
Is there a natural like construction of the map for that corresponds to the meet?
Not that I know of off the top of my head. The most natural way to understand the meet, and I should probably have said this too, you're looking at any time that you have two blocks that intersect, but instead of saying now I can differentiate both things, or now I can differentiate more using my partitions, you're saying, oh, now I know even less, right? So my partition X identifies some things, and if that partition overlaps with some other partition, this new partitioning joins all that together, or globs all that together, so to say. I don't know what a nice way to give this as a map directly would be. That is something that I've thought about and that I'm trying to think about because, as I mentioned later, I'm going to try and make this more categorical. But yeah, I don't know yet. But that's a good question. It's a very interesting question. Yeah. Eraser. Okay. So, what I've been kind of making use of here implicitly is the bijection between an equivalence relation on a set, partitions of that set, and surjections onto the partitions. So let me mention that actually. Right, so I'm sort of using the fact that a surjection is given equivalently by partitions, and that's sort of what's lending the name here, but also equivalence relations. And also, if you've ever heard of these, apartness relations. An apartness relation is just the dual of a equivalence relation. It's not too hard if you know what an equivalence relation is to figure out what an apartness relation should be. I mentioned that because the literature for these types of lattices goes back quite a ways, and it's not always referred to in the manner that Ellerman has started referring to it in the past decade or so, under this idea of the partitions being the most important thing because it's what relates most directly to information theory. But if you want to look up other results about these kind of lattices, most of them are under the name lattices of equivalence relations. And typically the order given there is the other order, the dual order, where instead I would say y is bigger than x if it's refined by x. So just be aware of that small little change there. But there's a lot of results you can find by searching for equivalence relation lattice instead. And a lot of open questions that you can find. Okay? But here's what we're going to do. Just like in the case of, so to say, logical probability, where I say, okay, well, I'll just treat everything as uniform, and I'll say that I take the size of my subset over the size of the whole set as sort of a probability of picking such an object. We want to create a similar measure that we can use on these partitions. So what we do is we take all the pairs, UU prime, which are in the, well, let me say this. Let me say that I take all the pairs such that pi of u is not equal to pi of u prime. And I call that the distinctions, or the dits for short, of some partition pi. So I guess I should say that that pi is a partition for a partition pi. And so we call that the distinctions. So this is what we want to think of as really being measured by information theory. The distinctions. There we go. Okay. So this set, this distinction set, this dit set, this is what we will use as sort of the corresponding objects to a subset, in that this is what we will measure everything with respect to, of these dit sets. Okay? So, kind of taking the motivation that info theory is concerned with distinctions, and when we give a notion of entropy, we're trying to capture an idea of how much information you need to make these distinctions, concerned with distinctions. We are led to a definition of so-called logical entropy. Of a partition pi, given by, I'll write it little h sub pi, h is used a lot for entropy. And it's just like I said, it's the size of that bit set, and then just like in the case of probability, at least in the finite case, I'm going to normalize it by the size of the set of all pairs u cross u. So this is the new notion of entropy. Now, this notion isn't entirely new, so to say. Ellerman didn't invent this measure entirely. He did invent this representation of it, however, at least to my knowledge. So one thing that we should note here, though, we can rearrange this a little bit. The distinctions I can take and say, okay, well, that's equivalent to taking all the pairs and then removing the ones that are equivalent. So for instance, if I'm going to denote all the blocks that are given by pi as B, so I'll just say maybe overall BI in pi. When I say in pi, I really mean that we're a partition determined by this map pi. And I take all the pairs from things in the same block, and I subtract those from the entire set of pairs. I make this little adjustment because it gives us a nice way to rewrite this notion of entropy, as instead being given equivalently as 1 minus the sum of all of these block sizes over U cross U. And yeah, I'll write this out in 2 steps, actually. Okay. So I can do that pretty immediately. And the thing that we want to notice here is that each of these BI cross BIs over U cross U, those are, let me not go any further that way, come down here. Those are exactly the probabilities of getting a distinction if we make 2 draws. So I'm going to say that's exactly the probability of getting an element from BI squared, i.e. getting an element of BI twice in a row if we make independent draws. Okay? So this captures very nicely the intuition that we already have from information theory, that information theory is about how many partitions or distinctions or ways of separating things apart that you need to do in order to actually pick out a specific event. In this case, it's represented very explicitly as 1 minus the probability of getting 2 things in a row that are exactly the same. Okay. So I want to give just a couple examples of that calculation. And then I'll describe how we turn that into a similar notion for quantum information. Okay. So I'll just write up a couple simple little lattices of partitions here. There we go. If U is a 1-element set, then the partition lattice is pretty simple. It just consists of that 1 element, right? Though I do want to mention that because just to kind of harp again on the fact that there's a nice duality here, it is interesting to observe that the partition lattice on a 1-element set would be naturally isomorphic here to the sub-objects of the empty set, right? There's only one sub-object of the empty set, that's the empty set. So just to kind of point that out, there's a nice relationship there. Same thing for the 2-element set. The 2-element set's partition lattice looks like, well, I've got the entire set U at the top, differentiating everything. And I've got my 1-point set at the bottom, identifying everything. And since there's only 2 objects, those are the only 2 options. So in this case, the partition lattice is equivalent to the sub-objects of the terminal object, or the sub-objects of a singleton. So we can see that duality playing out there kind of nicely too. Okay. More interesting though, I'll do one last example with 3 elements because that actually shows some interesting behavior. So the first 2 pretty simple lattices, nothing really interesting going on. As soon as we hit 3, that's where we start to see some interesting behavior. Here my partition lattice has U at the top, singleton at the bottom, identifying everything. And in between, I can pick any 2 pairs and identify them. So I'll just write it like this, A, comma, and B, C in braces. So my two blocks are just A and just BC. And similarly with B and AC and with C and AB. I mentioned this example in particular because if you know any lattice theory, this lattice should look very familiar. This is sort of the canonical non-distributive lattice. I guess if I wrote it a little bit more neatly, it might look a little bit more familiar to people who've seen the drawing. So I'll just do this little sort of schematic down here. But yeah, so this is exactly the sort of example of a non-distributive lattice. So that's interesting. And that's sort of the context in which a lot of these lattices, under the point of view of them being lattices of equivalence relations, this is sort of the perspective that they were sort of originally studied under. In particular, they were used as very ready examples of non-distributive lattices. By the way, very funny story I read while I was researching for this paper. American mathematician Charles Saunders Peirce, if you've ever heard the name, he was also a logician. He wrote a paper once and he said that every lattice is distributive and he could prove it, but he couldn't fit the proof in because it was too tedious. And then a whole bunch of European mathematicians sent him specifically this example. They were like, are you sure about that? I just thought that was a very funny story. Okay. I'll just move over actually. I'll probably need the space. Always nice to see a famous mathematician make a mistake because then I can feel at least a little bit better about mine. Okay. So now let's try to modify this idea to apply it to the quantum scenarios. So let's let F be some self-adjoint operator corresponding to some measurement we might make on a quantum system. So it's some self-adjoint operator on some Hilbert space H, some complete inner product space. Okay? And let's suppose that I have all the eigenvalues. I'll say phi1 through phi(m), right? So that's just the spectrum of my operator F. And I'm going to let U be the corresponding eigenbasis. And I'm just going to use n for the dimension of my Hilbert space. I'm going to worry mainly about finite dimensional ones. So let that be the corresponding eigenbasis for F. Okay. And let's make a partition of that basis. And I don't think I gave this a name here, but I'm going to write pi equals so that I can refer to it. So I'm going to take blocks that are given exactly like you might expect, where each bi, and my I here is running from 1 up to m. Each of those corresponds to the eigenspace. Well, I should say that's the eigenbasis of the eigenspace of the eigenvalue. So I make a partition of my basis based on which basis elements end up having the same eigenvalue. Interpreting that in terms of actual measurements, actual quantum measurements, that means I'm identifying things if they would have the same measurement result, right? The eigenvalues are the measurements we might actually observe. And so if they have a higher dimensional eigenspace than just 1, there's different vectors corresponding to that same measurement value. So then this partition gives immediately a nice direct sum decomposition in the form of just taking the spans. Oops. Here we go. Taking the spans of all the vectors inside each block. And this notion of direct sum decomposition, which we can pretty easily relate back to actual measurements we might want to do. This is going to be our, I guess, so to say, linearized version, vectorized quantum version of this partition lattice that we had before. Okay. So I'll refer to that lattice as just the lattice DSD of H, consisting of all of these direct sum decompositions. And for each one of them, I can associate them to a measurement if I want to, but we'll just kind of operate on them as if they're just direct sum decompositions for a second. So this is the quantum analog of the partition lattice. Okay. And just as in the case of the quantum event lattice, which I've spoken about previously, the quantum event lattice, aka an orthomodular lattice that's complete and atomic, corresponding to closed subspaces of a Hilbert space, those lattices are equivalently characterized as so-called partial Boolean algebras, because those we can take and restrict to just the subspaces that are orthogonal, and it behaves just like a lattice of subsets would. You don't even have any behavior that you would normally see from the sort of vector space structure. There's a dual notion here that is a similar sort of partial lattice kind of decomposition thing. Okay. Ellerman has shown that, I wrote algebra, but I'm going to say lattice, that the lattice of direct sum decompositions of a Hilbert space can be thought of as a partial partition lattice in much the same way that the lattice of subspaces or closed subspaces corresponds exactly to partial Boolean algebras or partial classical lattices. Okay? Because any particular basis I pick, any basis I pick for H, I'll call it U, this always gives a maximal partition lattice and really, if I restrict this to being an orthonormal basis, then the relationship with the subset lattice or the subspace lattice, excuse me, the subspace lattice is even more direct, because in that case, it is exactly orthonormal bases and subsets of those that give you your Boolean algebras, your Boolean subalgebras in the subspace lattice. Okay? So we get a maximal partition lattice, which is really just the set of everything underneath U. All the subsets of U as just a set of basis elements. Okay? So, this is the sense in which we'll understand a direct sum decomposition as being a partition in a different way, in a sort of linearized way. Instead of actually taking a subset partitioning of the vector space itself, I'm going to think about the ways that my direct sum decomposition corresponds to partitioning different basis elements into different pieces. Okay. So each direct sum decomposition, say pi equals, I don't know, maybe a bunch of little bi's. This corresponds to a partition of the basis elements of some set of basis vectors. Okay. And so just like in the classical case where I had this notion of distinctions, I can define so-called maybe quantum distinctions or qubits, quantum distinctions of pi. And what we end up doing, in the classical case, right, I was taking ordered pairs of points. Here I'm going to take tensors of points. I'm going to take the tensor of any pair of basis vectors that are distinguished by the partition thought of just as a partition of the basis elements. So I'll write pi u maybe to mean the corresponding partitioning not into the direct sum decomposition, but to the corresponding basis vector sets. So my qubit space is just the span of all the distinctions that I would have in the classical sense. I'll go ahead and write this. I think I already said this out loud, but observe, of course, that a particular pair is given in such a quantum distinction if and only if they have different eigenvalues under some operation that's being considered. So ui, uj have distinct eigenvalues. Okay. So this is our linearized version of making distinctions. And similar to how I was able to rewrite the classical case as being really the probability of taking two distinct draws and getting something different on each draw from two independent draws of the same set. So in the same way that the sort of classical logical entropy, I said that that was sort of the probability of drawing distinct pairs. We want the quantum analog of that to be sort of the probability of drawing two distinct measurement results if we know we started at the same state. Not the same system, of course, because the state changes under the measurement, but the same state. And so we define this sort of quantum entropy, maybe I should say H sub Q just to distinguish it. Okay. Yeah, I'll skip that a little bit. Okay. We can take this and we can just directly translate the relationship that I used when I transformed my bit set into an expression that made the probability of distinct draws more evident. So if I have some state corresponding to some density matrix, I'll instead do 1 minus the trace of rho squared. Right? The trace is adding up all of these different probabilities. Squaring that state is putting it into this sort of, you know, you're taking your probabilities, multiplying them together, seeing what happens if you want to say, do this and then have the same thing happen. Maybe that wasn't a clear statement, but I'm just going to move on. So yeah, so let me rephrase that slightly. So this represents the probability that we take two different systems that are in the same state, and we make two measurements, and we get two distinct outcomes. And so we were able to make some sort of distinction between those quantum systems that way. Okay? So, not much more I have to say right now. But I want to outline the direction to go in to start trying to make this more categorical. As I said, unfortunately, I don't have anything in the way of actual results for that right now. No, that's not the structure. That'll work. But I can still kind of outline where we can go. Okay? So In the same way that we look at a quantum event lattice, and as I said, for instance, the subspaces of the Hilbert space, it's a partial Boolean algebra. It's a bunch of Boolean algebras glued together. I'll say partial classical algebra, partial classical logic lattice. Okay. There's a natural way to take your complicated subspace lattice of some Hilbert space or some other vector space and think about it entirely based on how it's put together from all these classical pieces. And the way we do that is by defining this thing that I usually call the context category of my Hilbert space H, or of any orthomodular lattice, really. This is all of the sublattices of the closed subspace lattice that are classical, that are Boolean. So for instance, if I'm thinking of my subsets of the Hilbert space as corresponding to projections onto the closed subspaces, which I can also think of as being measurements of some quantum system, then the sublattices consisting of commuting projection operators is the same as the sublattice consisting of orthogonal subspaces. Both cases, that's a Boolean lattice, a classical logical lattice. Okay? And then we do a nice trick where we assign data, I'll put this in quotes, classical sublattice wise. One also sees classical, or one also sees commutative subalgebra wise. But since I'm doing things in terms of lattices, I'll say classical sublattice wise. And what I really mean is that I take my contexts and I assign them sets of data in a functorial way. Okay. So if I do this, then it can be shown that one, you can phrase everything you want to say internal to this notion of classical sublattice-wise assignment. And so everything you would normally want to say about a quantum system can be phrased as a classical property of this array of classical pieces of the quantum system. That's been established over the past maybe 10, 15 years or so by the work on the Topos theoretic approach of quantum mechanics. I'm not going to elaborate on all of that right now, though. Okay? But here's where I'm going to end. Sort of a research outlook for how I am proceeding and how I am trying to reconcile some of the different moving parts here. Okay? So the first one, and the one that I find the most interesting, is the one directly related to taking everything and thinking of it relative to classical subpieces. And so the first question that I want to answer, ideally by the end of the semester, but hey, fingers crossed. Can we understand the direct sum decomposition lattice in a similar way? So as classical partition, subpartition lattice wise. I'll say subpart lattice wise. Okay. So that's my probably most interesting question, I think. Can I take my direct sum decompositions? I know that it consists of a whole bunch of maximal partition lattices in the classical sense. Can I do this same trick where I parameterize everything over the classical subpieces? And in the same way, do I recover all the information I have in the direct sum decomposition the same way I recover all the information from my orthomodular lattice of subspaces? Okay. Now, a bigger, broader open question, harder to answer, but I'm still going to be thinking about it. still going to be keeping me up at night. Is there a categorical version or translation or something of these partition logics? Okay. So I have a nice categorical translation of most other logical systems that I'm interested in particular, all these Boolean lattices that I've mentioned. They can all be embedded as sub-object lattices in some category. And we can always do this sort of categorical logic trick where we interpret theories in random old categories with enough structure by just pretending everything in the category was a set and pretending all the maps are functions. So we know we can do that. That's a very well-established part of logic, is categorical logic like that. But there's no characterization yet of what that would look like for partition logics. So we would want some sort of system where the natural interpretation was not injections and sub-objects, but is instead surjections and quotient objects. Okay? A related problem, still an open question. I'm very surprised actually that this is still an open question. Is there a Hilbert system for this logic? If you've never heard of what a Hilbert system is for logic, then it's the only system you've ever used. By a Hilbert system for logic, I mean, here's a bunch of rules that they satisfy, now deduce everything you can. This is the way you probably thought about, say, group theory or whatever. You think about these axioms and you think about deriving things from them, right? So that's the notion of a Hilbert system. And it's unknown if there even is a good Hilbert system, much less any, for partition logics. Equivalently for equivalence classes, or equivalence relation logics, those kinds of lattices. There are some characterizations, some presentations that aren't Hilbert systems, but they're more tree systems and things like that that aren't so easy to translate, and which don't quite give you a good sense of the way the logic works. They just kind of give you a sense of how some of the basic formulas fit together. So I think these two questions are pretty highly related. In particular, if we want to have a notion of partition logic that we can interpret in an arbitrary category, if I want to interpret this as a lattice of quotient objects, I really do need to know what those lattice operations look like in terms of identities on the joins and the meets. So that's what we would really be looking for a Hilbert system. We would want to know how the meets and joins interact. Do they distribute over each other? The example I gave earlier shows that's not true, so we know we don't want that in there. But there is no nice direct characterization of what makes a lattice of quotient objects or of partitions or equivalence relations or what have you. Okay? And then the last thing I want to mention is the sort of actual direct quantum information theoretic question that I'm kind of keeping in mind as I think about these. Okay. There's a notion of informationally complete sets of measurements. So I'm using this abbreviation, symmetric, informationally complete, positive operator value measure. What do I really mean here? I mean having a system of measurements for a certain quantum system that is, one, informationally complete in the sense that all of these operators span all of the self-adjoints. So that's what I mean by informationally complete. And by symmetric, I mean that the pairwise probabilities are all the same. So for instance, in the case of C2 and the picture of the projective space on C2 as the block sphere, it's sometimes called, this looks exactly like taking a equilateral tetrahedron and embedding it in your Hilbert space and seeing it arise in the projection lattice, or sorry, in the projective space. Okay. So this is a really interesting open question because it's essentially just a question about embedding simplices into Hilbert spaces. And it's still unanswered. In fact, I want to say no dimension higher than 54. It's known if these even exist at all. Beyond dimension 5, we don't know if there's, so to say, enough of them. There's theorems showing that there either is the dimension +1 of them or less than the dimension -1 of them. There's some nice theorems that show some bounds on counting them, but it's an open conjecture that you can always find n+1 of these symmetric informationally complete measures. Okay? So can these be captured? My thinking is that they can, because once I translate everything into this functorial language, I can equivalently say that I'm trying to find a certain relationship to the simplex category of all maps from simplices into sets. Question mark. Okay. So those are sort of the big 3 guiding questions that I'm trying to answer as I look through all of this. Can I do this same trick that's already been done on direct sum decompositions? Can I find a categorical notion of partition logic, or even a direct characterization in terms of axioms on the lattice itself? And can I use this to understand the way that symmetric informationally complete measurement systems arise in different Hilbert spaces of arbitrary dimensions? So I'm going to end there.
So thank you very much. Let me just stand here. And are there questions from the audience in here or the external audience?
I think someone sent a chat question.
Oh, there's, let me just, David, is there anything, another entropy that, let me just open this. Is there another entropy, that logical entropy found by subtracting the square of the probability corresponds to? Is it a measure of quantum state impurity?
Yes, yes, great questions. Okay, so for the classical case, that measure has been studied not under the name of entropy, but it is studied as a notion of diversity in a population. For instance, that exact formula is used in studies of biological systems to understand the diversity of different species. So that formula has arisen in the past. It's never been quite called an entropy. This is the first time I think it's been referred to as an entropy, but it has occurred in the past. Regarding the question on purity, that is exactly what this is. Yeah, that's a great thing to recognize. If a state given by a density matrix is pure, then rho squared is just rho, and the trace of rho squared is just the trace of rho, which is 1, and you get 1 minus 1 is 0, so the state's pure. And in general, this measures a sort of idea that you're far away from pureness if you're farther away from 0. Yeah, so that version of it for quantum systems is already studied somewhat under the guise of being a measure of purity. Yeah.
Thank you.
Further questions? Yeah, please say it loud that we can, it's on the.
Yeah, so I'm curious, so the row in the density matrix, that doesn't depend, how does it depend on pi? How's that related to pi?
So pi is some partition of my my basis vectors, and rho is a state corresponding to, in that same basis, what the probabilities of being in each of those state vectors is. Maybe one thing else I should mention, this is more, I guess, in response to the question that David Jonas just had too. There's also a way to turn these entropies into the classical entropies. Ellerman calls this a bit transform. And I mean, it literally is just taking the formulas and replacing the information notion that we got with the log base 2 instead. That is also sort of on my mind as a research question because I don't think that that's precise by any stretch of the imagination. He just sort of has a table and is like, well, this looks like this, and this looks like this, and this looks like this. So it's also sort of an open question if this notion of logical entropy can be more directly related to entropy other than just noting similarities in the form.
Thanks. Other questions? Okay, thank you very much, Howie, again. And the next talk will be on geometric quantum mechanics. It will be announced via the math physics list. Thank you. Let me